Okay, so hello everyone. My name is Leticia Cugliandolo, so let me introduce. And Julian asked me to introduce myself, so I guess the most important thing I have to say about me here is that I have been the director of this institute for 10 years, and I stopped a year and a half ago, right when we finished the renovation of this building, which I hope you like and you enjoy. And so I'm very happy to be back and to be able to be on this side of the blackboard this time and give you some lectures. It's going to be actually a mixture between a lecture and a seminar. I have only 2 slots, so it's going to be mixed between the blackboard and some slides. And compared to the title that was initially announced in the program, I'm actually going to talk about something else. Perhaps Jorge is going to touch upon effective temperatures in his lectures. I'm not sure about that. But in any case, I'm going to describe the different problems in active matter. And so the title, let's say, of my talk will be Phases, or if I could say dense, active matter in 2 dimensions. So you already heard in Meharan's talks and in Professor Shelley's talks that 2 dimensions is special. So you will see more of the specificities of 2 dimensions in my talks. And actually, today's talk will be completely devoted to talking about rather basic features of phase transitions and phases of matter, passive matter, in 2 dimensions, which constitutes a big block of classical physics, but that is not so much discussed in normal lectures, in master courses, let's say. At least I haven't studied these during my studies many years ago. So the content of my talks is perhaps already available in the webpage, because I have almost finished writing the chapter. The first part of the chapter is finished, the last part is not so definitive. But the part that concerns today's talk, it's already there. The way in which I present it now, today, on the blackboard is a little bit different from the way in which I have written it, but okay, it's just complementary. I'm going to use the blackboard, but I'm going to show some figures and sketches that I cannot draw nicely on the blackboard with slides. And the new work, let's say, the recent research work I'm going to describe has been done in collaboration with the group of Giuseppe Gonella, in Bari. He has many excellent students who have been working with us over the last 5 years, roughly, on active matter problems. But I also want to mention Julian, whom I see sitting over there, who has done work which is very connected, related, and similar to what we have done. So you can also talk to her today or later about the content of today's and tomorrow's lecture. So the motivation of what I'm going to do is to try to understand, well, the phases of matter, today passive, tomorrow active, in 2 dimensions. So I guess you have been exposed to problems of phase diagrams, phases. In particular, I'm going to be concerned with problems in which there are particles, or could be more complex, say molecules, in interaction. So say that there will be n of them, that they will be confined to some volume V. So these 2 parameters are easy to understand. N is the number of particles, V is the volume of a box where I put my particles. And then when one draws phase diagrams, one uses other control parameters. That could be temperature, could be pressure, depends a little bit on the way in which you want to present and visualize the behavior of the system. Well, it turns out that in active systems, systems which are kept out of equilibrium, as we will discuss a bit more in detail later, neither temperature nor pressure are so well-defined quantities. One can say a lot about them, but I will not. But I just want to say that there is a lot to say about them, and probably there will be other courses that will touch upon definitions of pressure, definitions of temperature, and so on. Let's forget about this for a moment, and what I'm going to do is I'm going to just start by recalling the generic, say, phase diagram of passive systems where temperature is well defined. In a setting in which I'm going to put here the global density or packing fraction. So this is going to be number of particles over the volume. So I'm going to use the word packing fraction. Or density exchangeably. And in the horizontal axis, I'm going to put temperature. Okay? So a little bit schematically, one knows that at high temperature, one expects very disordered situations. One expects gases or liquids. So at low density, high temperature, it's going to expect a gas. Bit higher density, still high temperature, one expects a liquid. In between these two, there could be a region with phase coexistence. So I'm going to draw something like that. I'm going to come back to this later in the talk, where there could be coexistence between liquid and gas. But then if I go to lower temperatures and higher densities, I will expect up there, I want to erase to make a little bit of space. I will expect up here a solid. I would expect the liquid that comes down somehow. So there should be something going on, a transition between the solid and the liquid, that it's typically called melting, and I'm going to use this color for that. And most of my discussion today will be concerned with the discussion of how the melting arises in two-dimensional systems. Okay? So just to recall, in 3D, there is consensus that this is a first-order phase transition. I will recall phase transitions later in my talk, but just as an introduction now. But in 2D, this is not so clear. So the nature, say, of melting is a matter of debate and a matter of studies and so on. So this is not zero temperature. There can be things going on here. So I'm going to be concerned about, intermediate temperatures between inverted commas, how the system goes from the solid to the liquid, and what is the mechanism for this melting transition. Okay. Now, if you're used to studies in active matter, you have seen something like this, reversed in this way. So looking like that. So, okay, let me be a little bit sketchy. And probably you heard about MIPS, and you heard about a control parameter here that has to do with activity, some measure of activity. So I will try to link my discussions about melting and MIPS by the end of the lecture today, but I'm just saying this as a matter of motivation and introduction. Now, the approach that I will take and the way in which I'm going to discuss things has a background, and the background is statistical physics. From the talks that you have heard until now, well, you've seen, and I've seen also, that the scope of the school is quite broad. So you heard about fluid dynamics, you have all these introductions on fluid dynamics and so on. My language, let's say, will be the one of statistical physics. And since I guess that the audience is quite heterogeneous, I will try to be quite introductory and, just stop me whenever you don't understand a word or you want a definition or you want clarification. I will try to be basic in my presentation without spending a lot of time doing calculations on the blackboard, but if you want more details, just let me know as well. Okay, so why 2 dimensions? 2 dimensions is interesting because it poses interesting questions from a fundamental point of view. But it's also interesting because there are, of course, applications and realizations of matter in 2D with films of all kinds in condensed matter physics. But there's also interest in the context of active matter because you can, for example, put your bacteria in a dish, and then these bacteria are moving in a 2D system, which is confined to some surface instead of a volume. But then I can talk in the same way about density, surface density in this case, and discuss these 2D problems. Okay. Now, if I talk about phases, phase transitions, I have to say something about how I'm going to describe these theoretically. So let me go back to the basics and start from the beginning, and I'm going to draw a sort of timeline here and start with Landau in the 30s that presented a general scheme to describe phase transitions. And this general scheme starts with the proposition that one has to identify an order parameter so some observable that takes different values in different phases in the phase diagram and then distinguishes the phases. Propose for it a free energy density. Meheran already talked about this a little bit this morning. So a free energy density, how does one proposes this one? Well, based on symmetries, based on something that one knows already about the behavior of the system. A little bit hand-wavingly, it's a phenomenological approach. And this free energy density will be a function of this order parameter. So let me write it this way, and let's call O the order parameter. And it will take different forms in different phases, and the minima of this free energy density will tell you about metastable states or stable states that the system likes to be in, depending on the control parameters in the problem. So phase transitions appear as changes in the form of this free energy density and changes in the values that these minima take. So let me briefly summarize the main cases, because I want to have this background to discuss more complex situations later on. So one of the cases that will be of interest are first order phase transitions. So within this scheme, these correspond to this f of O taking a form that, say, for some value of the parameters has a single minimum here and another one higher up. So this is the stable, this is the metastable. So let me put an S and an M here to distinguish them. And O are the values OS and OM that the system takes in this metastable and stable. Now, one changes the control parameter, and the form of this free energy density changes. And it comes a value of the control parameter in which these two are at the same height. This is the phase transition. So let's write phase transition. And then one can continue changing the control parameter, and the one that was metastable becomes stable, and vice versa. So the system changes from wanting to be at this value of the other parameter to wanting to be at this other value of the other parameter at the phase transition. And if one writes in a plot control parameter the order parameter, then there will be a jump in the value. So say that this one was smaller before, and then there is a jump like this. Okay. So there is a discontinuity in the value of the parameter at the phase transition. This is the phase transition here. And I should have included averages of this O to say that this occurs on the average values, but okay, I'm a little bit sloppy with the notation here. So these are the main features of first order phase transitions that I want to highlight here. I want to highlight also two other features that are not that are a little bit less common and less discussed in the literature, which is that usually these phase transitions are discussed when there are two states in competition, one and the other one. But this is not necessarily the case. There can be situations in which the competition is between one and many. So imagine that instead of this, there was something like that with many minima that are higher up, and that they all come at the same height at the phase transition, and that they all come, the good ones, after the transition. So many minima here. And well, the reason why first transitions are usually discussed in this context of only one metastable state and another one in competition with it is that usually the example that is used is the one of the Ising model under a field, right? When one changes the field, the system changes from minus magnetization to plus magnetization. And this is the example of the textbooks. But there are other cases, other models which are a little bit less conventional and that will be of relevance for me today. Like, for example, I give you an example, Potts models. With Q states larger than 4. If you don't know about this model, it doesn't matter. Can tell you about it later on. But there are examples of statistical physics problems where you have this kind of situation, and the competition is made with many equivalent states after going through the phase transition. Okay. Now, other phase transitions are of second order. So these are continuous. There is no jump in the order parameter when the system goes through the phase transition, because the way in which the free energy evolves is that it goes from a single minimum to a flat situation to two minima of this kind, for example, if there are two in competition. And if I plot the order parameter as a function of control parameter, it will do something like this, and then like that. And this is the phase transition. In my plot, it goes from 0 to a different from 0 value, because I'm taking 0 here, but okay, this is just an example. Now, what do I want to highlight about second order phase transitions? I want to highlight that the order parameter takes a non-zero value in this convention after going through the transition to the left side of this phase here, while it's 0 on the other side. But I want to highlight more the fact that I can characterize the phase transition via correlation functions. So, in general, I can define the correlation function in this way, where delta O of R is O of R minus the average of O of R. R is a position in the system. So if I have my system with some system of coordinates, R is this. A vector that this is my system. And R prime is another one. So correlation functions tell you how much resemble the fluctuations around the average value of your other parameter at different points, separated at a given distance. So these correlation functions, what do? Well, close to the transition, they decay exponentially. There will be some power law here that I'm not writing. This is what is called the correlation length that diverges at the transition, and it diverges as a power law at this critical point here. So things to know is that, okay, I can define these correlation functions. They behave exponentially apart from power law correlations exactly at the critical point. And the correlation length diverges on both sides of the transition as a power law of the distance from the critical point. So if I say that I call P the control parameter, this psi above or below the critical point will go like P minus PC to the minus nu above or below. This is an exponent. I'm just calling it nu. Okay. Compared to what happens at first order phase transitions, I could also compute correlation functions. And what I will see is that these correlation lengths will be finite. So this is another thing that I want to highlight here. Finite correlation length. Okay, but this is not all the kind of transitions you can have. Actually, there are other kinds of phase transitions which are even more interesting, and that are phase transitions for which there is no other parameter behaving in this way. So taking a non-zero value on one side of the transition, or neither behaving in that way over there, taking different values on the two sides of the transition. There are transitions which are called topological phase transitions. Or infinite order sometimes. And their characteristics are that, as I said already, I cannot find or cannot define an O having a behavior of this kind. The transition is driven by what are called topological defects. What are topological defects? So they are exotic excitations above the ground state. So imagine that you have a ground state which is the best configuration you can have at 0 temperature. And there will be fluctuations induced by temperature in your problem. And there will be simple fluctuations, which are little fluctuations above the ground state. But at certain temperatures, there could be other kinds of fluctuations, which are not, it is not possible to smoothly transform them into the simple smooth fluctuations that I mentioned before. So I will give examples about this. For the moment, say it with words is well, quite impossible to understand what I'm saying. But I will give you examples relevant to the problems that I'm discussing a little bit later today. So what I want to highlight is exotic excitations. I can also compute correlation functions in these problems. Correlation functions of some observable. And what I will find is that well-chosen observables, although their average is 0 in the thermodynamic limit, meaning system size going to infinity or n number of particles to infinity. So although this expectation value of this observable will be 0, the fluctuations of it, or the correlations of it, will not be trivial, and they will have different behavior on the two sides of the transition. Yes? I will tell you later. So for the moment, it's just a word, and I will give you an example later. So these correlations, what do they do? So on one side of the transition, they decay as a power law with a parameter, with an exponent, sorry, that depends on the parameters in the problem. So depends on temperature and depends on some energy scale that is typical of the problem. I call it in J here to make an dimensional object here, and hence a number. And on the other side of the transition, they decay as an exponential with a correlation length that diverges at the transition exponentially. Okay, so this psi of t will go like E, or of P, say the control parameter. Now I changed to T, sorry. Let's still call it P. P minus PC to the minus some exponent here. Okay, so you see that when P goes to PC, this is 0, but there's a minus over there. So this diverges exponentially. Is it okay what I'm saying? My signs? It's a plus, yes. Okay. Okay, these R, which I wrote here, I forgot to say that it's just R minus R prime. The modulus, so is the distance between these 2 points. This is R. The same R I'm talking about here. Okay, so these exotic excitations, what they do is that they change the behavior of the correlations from decaying very slowly, like a power law, to decaying normally in what I expect to be the disordered phase, meaning exponentially, like here. So here, in the phase in which the other parameter has a 0 value, these deltas are not necessary because the average value is 0, so it's just the O that I'm correlating, and hence I have an exponential decay as here. Yes? Exactly. So, yes. So for finite size systems, so if n is not infinity, this will go like a power, typically, a power of the system size. And then, as Olivier says, it's more precise, and what one should do is to put the deltas here. Yeah. And then presumably there will be finite n corrections to these forms as well. But okay, so which is the model that realizes this phenomenology? And the model that was treated by Costales and Thaules, so let me erase, and that this is a Nobel Prize paper. Somebody was asking about Nobel Prize results yesterday over dinner. So this is a Nobel Prize result. So mid-70s. Let me put it here somewhere. This was observed in a spin model in 2 dimensions. So it's a model where there are planar spins. So these SIs have 2 components. And they live on the vertices of a 2-dimensional lattice. Let me draw a square lattice. So what they can do is they can turn on, well, something like that. Okay. So there is a ferromagnetic interaction in the sense that they want to align. You see that the configuration of spins that minimizes the energy is the one in which neighboring spins are aligned in the same direction. This is a sum over nearest neighbors. on lattice. So at 0 temperature, where no fluctuations will be present and where the minimization of the free energy corresponds to the minimization of the energy, the system wants to be totally aligned. So say, I don't know, I choose this direction, or like that. But if one then switches on temperature fluctuations, what will happen is that the spins will start fluctuating a little bit. So the smooth fluctuations I was talking about will be weak rotations of the spins from side to side, let's say, very smoothly. So these are called spin waves. If one writes down the continuous approximation that corresponds to this Hamiltonian here, that I will do in a second, then one realizes that the correlation functions of the spins displaced at the distance r behaves like this, if only these kind of fluctuations are allowed. So what I'm saying here is that if I rewrite this Hamiltonian in terms of the angle formed by the two neighboring spins, so let me draw it here. So if this is the spin I and this is the spin j nearby, well, I translate here, and this is the angle theta ij. So I haven't done anything yet. But if now I assume that theta ij is very small, one can expand the cosine write something like this, drop higher order terms, and taking a continuum limit in which one takes the lattice spacing to 0 and does some other tricks. This first term is irrelevant because it's a constant. This second term will go to the Gaussian theory that Mejeran was talking about yesterday. Because you see, theta ij is a difference between angles. So with this, I never know how to call this one. Okay, the spatial derivative involved in this symbol here, acting on the angle, corresponds to this difference between the angles. It's squared because it was squared from the cosine. So this is the Gaussian theory that Mejeran was talking about yesterday. Only that the difference is that theta is an angle. So since it's an angle, it comes back to 2 pi after making a turn, right? So the periodicity, the discrete periodicity of the field theta makes a difference. And the difference is that, I mean, one of the effects of this difference, which is important to generate these exotic excitations, is that not only due to temperature there can be smooth changes in the spins of this kind, but there can also be other configurations, other excitations with respect to the ground state, which are called vortices. And that basically, I'm going to draw it in this way, correspond to spins that turn around some region of space. Okay, so this is not necessarily a plaquette. It could be, you know, around here, the spins are turning around the center of this region in space. And this kind of excitation with respect to the perfectly ordered state cannot be smoothly changed by just, you know, changing a little bit each of the spins involved into something like this. It's a different kind of object. And these are the topological excitations that give rise to the phase transition, changing the correlation from this behavior to this behavior. Working with this Hamiltonian alone, one will not be able to see a phase transition in this problem. One has to add these other excitations. Okay? And this is part of this Kosterlitz-Saules paper. And something else that they have done to justify that they really play a role is that they have done complicated calculations as well, but a simple one that it corresponds to calculating how much the free energy changes considering the free energy of a configuration with a vortex with respect to the one with the zero vortex, let's say. So to do this calculation, what you have to do is to estimate the energy of one such configuration. And it turns out that it's huge. It diverges with the system size. So you would say, well, this is not very convenient to create one of these excitations. But then you also have to compute the entropy associated to creating this excitation. And the entropy comes with a minus sign in the free energy, right? Because it's energy minus KBT(S). And since you can place this vortex in many places, so if you consider about the center of the configuration I have drawn here, and then you can place it, in many places in your lattice. If you estimate this, you estimate that, you realize that there is a finite temperature where this one wins with respect to the other one. Okay? So there is a temperature, KBTC, that a simple argument like this being finite, tells you that beyond this temperature it's good to have these kind of excitations for the system. And this is the defect-driven phase transition mechanism as a LKT. Now, if you want to compute this correlation length, then you have to do other calculations, go through RG methods. Not going to discuss that to justify this exponential divergence. But the fact that there is a phase transition, that there should be a phase transition, and there cannot be what is called quasi-long range order. So this is for all temperatures, can be suggested and justified with this simple argument. Okay. So other questions so far? Yes. Right. Okay, so if you create a pair of vortices and you do the calculation of the energy that costs, you will see that it doesn't diverge with the system size. So it doesn't cost much to create pair of vortices when they are nearby, when they are not far apart at a distance that scales with the system size. So in the low temperature phase, actually in this phase where the correlations decay as power laws, there are vortices, but they are paired. They are together. And you can also compute the density of these pairs, doing some more complex calculations than what I'm doing on the blackboard. So there is a finite density of pairs in the low temperature phase, but these are not enough to kill the quasi-long range order nor create a phase transition. They have to unbind, separate, and be seen as alone, as isolated, to drive the phase transition. Exactly. So if you look beyond the phase transition, you will see a finite density of isolated vortices. Vortices, not being paired. Okay, so, and this is Nobel Prize relatively recent one, and I have to say that Saules came here to teach many times. Actually, he came here as a student, I think. Yes, as a student, more than 60 years ago, also to celebrate his wedding as a honeymoon. And actually, when I started here being a director in the first or second school I was here, he came. Actually, he asked to come. He was not invited. He asked to he asked to come as a student. And okay, we said, well, we have to ask him to give a talk, no? No, not as a student. And the reason why he wanted to come was to celebrate the 50th anniversary of his wedding, because, okay, after after being married to his wife, who was with him, they came immediately here for the honeymoon. So anyway, sorry? Actually, Meheran Sid was a student in that school as well. Sid, yeah. Okay, so this is the, say, standard picture of these topological phase transitions. But in the 80s, let me write here. In the 80s, Eitan Domani and collaborators noticed that if instead of choosing this potential for the angles in the problem, they chose a potential which is steeper in the angle. So what do I mean by this? The cosine is, well, some function that looks something like this as a function of the angle, right? With some periodicity. Now, if instead of choosing a function like that, they chose a function like this. Okay. Well, you see the steeper, with the steeper wells. And the way in which they parameterize this problem is by working with well, I think I'm writing it correctly. Let me check. This is the function they chose. Yes? So there is a parameter p here, nothing to do with the control parameter I was using before. P is another parameter here. So you can check that if p squared is equal to 1, apart from some constants, you go back to the cosine. But if p is large, and in particular they chose p equals 50, I think, then you make this steep potential. And then they did simulations, and what they saw was that the transition was not of this kind. It didn't go from this power law regime to an exponential regime with a exponentially diverging correlation length, but it became first order. From numerics. There were many studies of numerics that studied this problem in more detail and confirmed in different ways that this model for sufficiently large p seems to undergo phase transitions of the first order that I was describing before. And more recently, in the 2002, 2005, a mathematically oriented group, let's say, has proven rigorously that indeed for sufficiently large p the transition is of first order in this model. So this is Schlossmann and Van Emt. So I will not go through the proof. I mean, I cannot go through the proof. It's a mathematical proof where what they do is they prove that they exist two Gibbs states, two well-behaved Gibbs states of the form of being minima of free energies, as I was drawing beforehand, that coexist in some region of temperatures for p sufficiently large, and then these two are the ones that are in competition, and then one wins with respect to the other one on each side of the transition. So on the other side of the transition, sorry. So it's a fact that this model for p large enough undergoes a first order phase transition. Now, yeah. Exactly. So it is still a transition between the quasi-long range and a disordered phase, but it's of first order kind. In their paper, they insist a lot upon the fact that their proof doesn't necessarily use the fact that it's a Costa-Ristaules-like phase, the quasi-long range order one, and that they can use it for other cases as well. And actually, they had used it in the past, the same arguments, for other problems. So that's not essential in the proof. Now, from the point of view of vortices, the proof doesn't say anything. What people have argued, again from simulations, is that what's going on differently from the smooth case of the cosine is exactly related to the question that was asked before. There are no pairs of vortices in the quasi-long range ordered phase. It's very it's not good to create them with this kind of potential, not even pairs. But it's from simulations. And what seems to be happening is that there are no pairs in the low temperature phase, and all of a sudden they appear. In the vortices appear, are generated at a given temperature discontinuously. They're generated in this way. So this seems to be the mechanism, but I'm not sure that it's settled and completely sure this is what's going on, but it has been suggested by different authors. Okay, so I have done in 45 minutes a kind of summary of, let me see how I'm in time. Oh, I'm okay. Of phase transitions and, really generic definitions and concepts that are going to be useful for me now. Because what I want to do is to discuss particle systems. So I want to, similarly to what I have done here, start from zero temperature crystals and see what does temperature on them. Does crystals continue to exist under thermal fluctuations in two-dimensional systems or not? And in case they don't, what happens? And which is the equivalent of the crystalline phase, and what's the equivalent of the disordered phase that will be the liquid, and what happens between them, and so on. So let me erase here. So as I said, I'm not going to do many calculations on the blackboard, so I'm going to give you some exercises that if you're interested, you can do. So now, let's imagine that you have a system of particles in interaction in 2D. So at t equals 0, you expect a crystal. So a crystal means that the particles sit on a lattice, so some perfectly periodic structure that breaks both translational invariance, continuous translational invariance, has only discrete translational invariance by the length of size of the step, lattice step, that I'm going to call A. And so let me draw it. So let me draw it in the square lattice case because it's the one that is easy to draw. So I have a square lattice with A here I have some system of coordinates here. To know the structure of the crystal for a generic potential V of R, say that this is the potential of interaction between particles sitting at the distance R, so it's a pairwise potential I'm thinking about. So this is already a difficult question. For generic V's, to know which is the structure that minimizes the many-body problem of the sum over all the couples of particles and so on, which is the structure that the system would like to take at 0 temperature, is a complicated problem. And in the notes, I give the reference, here it is, of recent review. Again, this is mathematical literature, but if you're interested, where this problem is discussed. But okay, forget about that. Let's assume there is a crystal. And to make my drawings easy to do, I'm going to make it square. So now the particles are sitting on the vertices of this lattice. So say that this is the position that I'm calling Ri of particle I, and that this is the position that I'm calling, well, Rj of particle j. So in capital are the positions of the lattice vertices. Now, if I switch on temperature, I expect this perfect periodic structure to modify. And I expect the particles to move a little bit and displace from these positions. Say, I don't know, I'm going to draw it separated to make, again, my drawings easy. Okay, so capital is perfect lattice, and lowercase actual positions. Now, the Ri's, one can parameterize as capital R plus a displacement. As displacement from its perfect position of the site I. Now, in the 30s, Peierls, again, and also Landau, thought about this problem, and they thought about the simplest possible model for this kind of situation, which is just to, if you wish, expand this potential and make it harmonic. So basically what they're doing is that they're considering that the interactions between a particle and each of its neighbors is given by a spring, Hookean spring. Okay. So now it's easy to write Hamiltonian for this problem. And, well, you can do it. And what will turn out is that, let's call V as above, the energy will have a ground state contribution that is just given by the positions of the lattice, plus a quadratic term in the ensemble of the UIs. Okay? I'm not writing it because it's long to write, but okay, basically what you will have is a sum of terms of the kind UI mu, it's called M mu nu, U I J J nu, something like that. Okay? And these u's are vectors as well, so let me put the arrow, and the arrow was here. Okay, so the i's and j's are the particle indices, and the mu's are the directional indices. So I goes from 1 to n, sorry, and mu and nu go from 1 to d. But we are going to be interested in d equals 2. Okay? Yes? Okay. Yes, indeed. Exactly. So here you should have sums over ij's that go over all the I and the j's. I agree with that. What you're going to do next is to simplify and assume that things drop off sufficiently fast for the potential here, so that you will stay with the nearest neighbors. So this will give you constraints. I mean, this part here I could write with all generality if I sum over I and j's, which are all of them. And then what you will do is to do approximations on this matrix, on this tensor, I should call it. I don't know, it has a lot of indices, on this object here. Okay? So all this discussion, you can have a look at it. It's done in a lot of detail in the Ashcroft-Mermin book. Solid state physics, I think it's called. And it's also very nicely done in an article published in the IHP, Institut Henri Poincaré Proceedings, I think it's called, by Pyers himself, around the 30s. You can find it on the web, it's available. So imagine that you go through all this and you simplify, and then you go to Fourier space because it's simpler, and you make assumptions, as Olivier was saying, concerning the range of interactions. In the end, basically, you will end up with the Hamiltonian, which is again the harmonic one that Mejeran was talking about. So under a continuous approximation, or continuous extension, I don't know how to call it. And then what you can do, yes? Okay, so I and j are the particle indices that you could also imagine as being the lattice side indices, because you can associate a particle to each side. And the mu and nu's are the space-dimensional indices, so the coordinates, 1 to 2. So if you are at this level here, and now you say that you assume that the u's are ruled by the equilibrium fluctuations, so that the probability of a u is given by the Boltzmann weight. So let's put the h of u here, with this h of u, and beta inverse temperature. Now I leave you as an exercise to compute. I think that Mejeran also gave it as an exercise to compute this quantity here. So the displacement of the mean square displacement of the displacements at distance r between them. And what you will see is that this object goes as kbt log r minus r prime. So actually the distance between the 2 points you're looking at. So say that you're looking at a point r which is here and a point r prime which is there, and this is the distance between the two. So the displacements of the particles that are sitting here and there grow, one with respect to the other one, with distance, slowly, but they do grow. And these diverge slowly again as a logarithm, but it does diverge with this. So this means that the system cannot sustain this crystalline order, that the particles will move around from their perfect lattice configurations, and hence there is no crystal into D, or better said, there is no harmonic crystal into D. So within this harmonic model, the order is destroyed by thermal fluctuations, and you see that this is proportional to temperature. So if I switch temperature to 0, this goes to 0 and it's fine. So it's temperature that breaks the order. So this was realized by these two people in the 30s. Okay, but now the question is this generic for all kind of interaction potentials, or is it peculiar to the harmonic approximation? And this was discussed by Mermin. 68. So Mermin came back to this problem, and he gave a generic proof for any V of short range kind that I'm going to write here. By the way, the Henri Poincaré article is written in French. So I don't know if Pyros wrote it himself or if it was translated. Okay, so what did Mermin do? What he did was, first of all, he gave a generic criterion for crystallinity. So what he said is that let's look at the Fourier transform of the density. So the density is just the sum over all the particles of delta functions of the position at which you want to look within the sample minus the positions of the samples. So this is the space-dependent density in the problem. Now you Fourier transform this, and you ask whether the Fourier transform of this, that will be, well, I'm not writing 2 pi's and so on, not writing factors of n or factors of 2 pi here. So the Fourier transform density, he said to have order of some kind, there should be some rho k, for some k, different from 0. So for example, think in terms of modulation, so the k that is different from 0 will tell you is the periodicity of the order that you're looking for. Now, what he did was he exploited a bound. Yes? No, it's the actual, and it's fluctuating one. Say that it's the fluctuating one, and that then you ask, indeed here, whether this is non-zero. Yes, thank you. So I define the fluctuating ones, and then I average. Yes, please. One. Yeah, exactly. Only one. Only one. For some, okay, for one, I should write to make it more precise. For one. And the other ones will be 0 because there is one, only one. The other ones will be obviously 0. But yeah. Okay, so what Mermin did is that he exploited an inequality, which is kind of Schwarz inequality, written in a different way, that it was due to Bogolyubov. I must say that I looked for Bogolyubov's paper and I didn't find it. I found something in Russian, so okay, that was not very useful. But so basically, this Bogolyubov inequality, what it does is it starts from Schwarz, Cauchy-Schwarz, this is Cauchy-Schwarz. By the way, some grandson, late grandson of Cauchy is from here and lives in Boston now. So anyway, it's another another side comment. So, and he's a friend of Claudio Chamon. This is why I know him. So, okay, so you have the Cauchy-Schwarz inequality, and what you do is you choose B to be the Poisson bracket between the Hamiltonian of the problem and some C. C is a function of the position. So think in terms of particle systems. A and B are going to be functions of, say, position and momenta. C also. H is the Hamiltonian. For the moment, you don't say which ones these are. And the averages here are the equilibrium averages. Boltzmann measure and so on. So it's a variation upon Cauchy-Schwarz. Now, what Mermin did is that he chose a C, which was convenient, and an A, which was convenient, in such a way that when you replace there, basically you find something like this. So you have a finite object on one side. You have the order parameter, the putative order parameter, here, which is this. And you have something that diverges in the infinite size limit. Okay, so if this goes to infinity, this is finite, this has to go to 0 in the infinite size limit. Okay, so he proved in this way for this problem that for all case, these are bounded in this way, and then they have to vanish. So there is a thermodynamic limit to be taken to prove this thing. But okay, if you want to prove phase transitions, you have to take the infinite size limit. The proof uses equilibrium. I insist upon that. And okay, so this is a generic proof of the fact that they cannot exist translational long-range order in two-dimensional particle systems with short-range potentials. Otherwise, this part breaks down. But then he also realized something else, Mermin here. He realized that this proof was applying to this observable, this order parameter, and that the harmonic model of piles allowed for a different kind of order, which is orientational order. So let me put it here. So here I'm going to give you another exercise, which is easy. Exercise 1 was shared with Meheran. Exercise 2 is mine. So what you can prove is that within the harmonic model, say that you take, so R here, so I should have, R is a point in space, it's not necessarily a, I should have used lowercase. Okay, so say that you take 2 points, which are nearest neighbors, because A is going to be a vector along the lattice. Say, just to make it simple, make it A times EX. And compute the correlation function between these, I mean, for this scalar product. So this is telling you about orientations between the difference in the displacements at nearest sites and at nearest sites somewhere else. So here, so you're now playing with 4 things, right? Say something like that. No, it's in the same direction, sorry, something like this. Okay? So you want to know what happens with this, and you will see that this goes to a squared times some number, probably. So this goes to a finite result. And, well, you can play with displacements longer at not necessarily the lattice space in here. So you will see that this goes to some finite result. It doesn't go to 0. So there is some order which is maintained. Oh, sorry, I made a mistake. So, yeah, no, it's okay. Yes. So the distance between the 2 points is large with respect to A. So you will have to drop some A's with respect to distance. I don't know who's asking me, but yeah, okay. So this is large with respect to this, to the lattice space. Okay, or yeah, or with respect to the, you're not, yeah, okay, this is what I mean. Okay, so I have 15 minutes, right? Or not? Roughly. I'm looking at that. Yeah. Okay, so this sort of finishes what I wanted to do exclusively on the blackboard. Because the rest, I want to show you what's the equivalent of the vortices in the context of these problems, and I cannot draw this on the blackboard, so I have to show it with figures that I have taken from other people. So, yes. The fact is that there cannot be any. So what Bogoliubov's inequality does is that it shows you that for all, so this is for all k, rho tilde of k. So you can plug in here any row of k, and for all you will have an inequality of this kind, and then for all this will be going to 0. So there will be, it doesn't exist any k that yields a different from 0 result. This is the short range. So if the distinction between short range and long range depends on the dimensionality of space. So it has to decay with distance sufficiently fast. I don't remember now the power, but faster than a certain power that depends on d equals 2 in this case, for this to be true. Okay. How do I switch on that from here, right? On. So this I can erase. So now, well, my timeline has been cancelled here. So what we have is that there's no crystal in d equals 2 at t larger than 0 for short range v of r. But there are solids. So what's a solid is something that, if you apply a force, say that you, okay, the definition is that if you place a solid over a table, let's say, which has some friction, and you exert a force tangential to the surface of this solid, it will deform a little bit. So it has a finite shear modulus, but it doesn't flow like a fluid, right? A fluid will go. So there has a finite displacement that you create with this finite force that you are applying. So this is a solid. And there are solids into D. There are objects like that into dimensions. So solids exist. Liquids exist. What does it happen between the two of them? And what happened in this timeline that I was trying to build is that, again, after KT, Nelson, Halperin on one side and Peter Young on the other, they built upon the results of KT, and they claimed that the way in which the transition between the solid and the liquid occurs has to do with the liberation, let's say, the unbinding of defects. Already KT talked about unbinding of one type of effects that I'm going to show you first. And then what they did is that they said that actually there are two types of effects that unbind at different temperatures, and that the transition between solid to liquid occurs in two steps. A first step, which is called the melting transition, that I'm going to call Tm, and a second step, which is the transition, the proper transition to the liquid, which I'm going to call Ti. And what happens is that in the solid, you will have no translational order, because this cannot exist according to Mermin. No translational long range order. Only quasi-long range order of the kind of the XY model that I described at the beginning. Long range orientational order there will be an intermediate phase between these two with something which is called exotic order or exotic phase. Let me call it exotic phase, that has short range translational order. So correlations decay exponentially. This is what I mean by short range. Well, here correlations decay as power laws. Here they don't decay, they go to constant. Here in the exotic phase there is quasi-long range orientational order, in the sense that it goes like r to the minus eta. Let me call it eta O for orientation, and psi O for, psi t for translation. And then when you go to the liquid, both types of order are not existent, let's say, and the correlations decay exponentially for both types of observations, both translational and orientational. Now, if this thing sees my computer, I can show you what I mean with pictures, which will be, oh, maybe it's my computer that doesn't have any more battery. No, yeah, it does. Is it there? Yeah, okay. So this was the phase diagram. So view and the full screen. Okay, so which are the defects, the things that correspond, play the role of the vortices in this problem? So the first type of, and I borrowed all these pictures from the web, none of them are mine. Some of them I quote the author, some I don't. So anyway, so the first type of defects that already Costa-Lizarraga talked about are called dislocations. So in this square lattice basically corresponds to adding a line of sites, inserting a line of sites until some point in the lattice. So you see here that there is this breaking of the direction of these two vertical lines here to make place for the other one. So from this kind of dislocation, what the system will do is that it will break translational order. It's clear that translationally something very strong happened here, but you can see that far away the orientation of the lattice is the same. It didn't change. So these kind of defects, this kind of modification, excitation, doesn't change the orientational order of the sample. It only does around the center, let's say, or the edge of this dislocation, but it doesn't do it far away. So these kind of defects are the ones which are going to drive the transition from the solid to the exotic phase in the actual cases. the actual systems. Notice that this is a perfect square lattice, that it doesn't really exist in 2 dimensions. There will be fluctuations because there's no crystal, but well, the scheme of what I'm showing is this one. Yes. Oh, because the Mermin-Wagner theory, this is something that it's always wrongly stated in the literature, and even myself I wrongly stated once, is that this theorem it's not really a theorem. I mean, what it's doing is that it's taking a observable, a candidate for another parameter, and it's showing that that one is 0. But it doesn't say anything about another order parameter. It only affects the calculation to this Fourier transform of the density. And it only tells you that the Fourier transform of the density will be 0 for all wave vectors. But then it will be possible to construct another order parameter that has nothing to do with the density. It's another function that I will define it later. And for that one, the bound doesn't apply. You cannot build a bound of the same kind for this other parameter. So there will be another parameter which will be non-zero, and for which the correlations will decay to a non-zero value. And for that one, symmetry is broken, and there is long-range order for the orientations. Am I clear? No? You don't look very convinced. So it's a result on one quantity. That it's a quantity which is a candidate for a certain type of order, but it doesn't tell you anything about other kinds of order which are possible in the system, and that you may not realize they exist until you look for them. So, yes. Yes. Exactly. So this is what I meant when I said it's wrongly stated. Exactly, this is wrong. And if you look in the literature, the only place where I saw it said really clearly is in Setna's book. In his lectures and in Setna's book, is very clearly stated that one doesn't have to cite the Mermin-Wagner theorem in the sense that you cannot break a continuous symmetry in 2 dimensions. This is not true. Exactly, yes, yes. So I'm not talking about the matic order here, only orientational, but yeah. So on an hexagonal or triangular lattice, which is going to be more relevant to what I'm going to discuss next, the dislocation appears here. So it's a line which is inserted there, and what you can see is that what I try to highlight here is the line that is added, and this central point, instead of having 6 neighbors as they do in all other cases, 1, 2, 3, 4, 5, 6, it has 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the effect of this extra line which is added is that when it ends, it creates a point-like defect with a side that has 1 more neighbor than the regular lattice has in all other cases. Again, in this case, in this picture, the angles far from this point here remain unmodified. If you look here and there, the angles are the same. Okay. So this is a line dislocation in triangular lattice. There are other kinds of dislocations, but okay, these are the more simpler to visualize. Now, there are other kinds of defects that you can create on uniform lattices, which change the orientation of the lattice, and these are called disclinations. So this I took it from a paper by Leo Radzichowski. So what he does here to exemplify this is that he has a square lattice, he takes away a square, and then sticks this end with this other end here. So you're turning your lattice in such a way that now the angles are completely different. So this kind of defect is changing the angles. Also the translational order, but also the angles. And for a triangular lattice, this is another example of a disclination that changes the angles, and you can see that the angles far away are different, and if you start counting, you will see that there are points within that have 5 or 6 or 7 neighbors. This is an example that if you have 2 disclinations put together nearby. If you look far away, the angles are respected. So this is similar to what we were asking before about having two vortices together. If you have two together at a finite distance, if you go look far away, then the effect is minimal, it's irrelevant. But if you had only one and you look here compared to there, then the effect is important. Okay? So when you have these effects bound together, far away they don't exist as effect is concerned, while nearby they are. So why did I say that the hexagonal lattice will be the relevant case for us? It's because I'm going to talk about spheres. So spheres, they like to order in 2 dimensions in a hexagonal lattice. So this is perfect order. And from the centers of the spheres, you see that you join them and you create an hexagon. And if you join the center of this one with the neighboring ones, well, there are 6 neighbors. So each center has 6 neighbors, and there are no defects in this picture. Okay, so maybe now what I'm going to do, I didn't finish what I planned to do today, but almost. Yeah, so, okay, so I will sort of stop now with a summary. I will come back to this tomorrow. I will quantify a little bit better what I meant by long-range order in one case, quasi-long-range order in another one, by defining the lacking order parameter for this exactic phase, for this orientational order. And I will show you that these correlations will behave in the way that you expect, in the sense that the correlations of this new order parameter will decay as a power law in this exatic phase and as an exponential in the disordered liquid phase. So they will be able to characterize the phase transition between this exatic and the liquid. Okay, and what we will do next is discuss some recent or relatively recent results by Werner Kraut and his group in Paris, including Julien, who have contested the standard picture of the phase transition between the exatic and the liquid that comes here below. So the standard picture of these people here tells that these 2-step transitions are both of KT kind, in the sense of having this correlation length that diverges exponentially at both transitions, both at this one and both at that one. While what Werner and collaborators found is that for passive disks in interaction, the second transition, the one between the exatic and the liquid, is of first order. And this is similar to the Domani's results for the XY case. So recall Domani's for the magnetic problem, where by changing the kind of the potential, they saw that the transition went from KT to first order. So there is lack of universality in these problems. I mean, it's not only the symmetry of the interactions that you have in the problem that defines or determines completely the kind of transition. By changing a little bit the potential, well, you could say a lot, but changing the potential here, but respecting the same symmetries, they found that the transition changed character. And what they find here is that, again, not by changing the potential, but by looking in more detail to the behavior of the problem with extended and very complex numerical simulations, they found that the transition between the exatic and the liquid is not, as it was expected, of KT type, but of first order. And what we'll do next is to include activity and try to see how these pictures of phase transitions in the passive case survive or don't survive, or how the activity modifies the phase diagram of the active problems now, well, under these similar conditions, but by injecting energy into the system. Okay, so this is the plan for tomorrow. So I will stop now. Thank you. I don't know if there are questions or comments. Yes. the mechanical properties. Uh, I would say that there should be, but because I mean, having different kind of orientational order, I guess that you can do different things by trying to turn this sample in different ways, and they will respond differently. But I'm not an expert, and maybe Olivier should know more about that. Yeah, that it's a liquid. Yeah, it's more like a liquid. So, but maybe there is something that you can do to it. Well, I don't know. Yeah, I don't know. Well, okay, stop here.